Hello, this is Jose Luis here at Parametric Camp, and welcome to this new hands-on exercise on the course Advanced Development for Grasshopper. In this exercise, we're going to be developing a bunch of Grasshopper components that are specifically designed for vector operations. So, as you saw in the previous video, we have construct point, construct vectors, lines, and plane. But in this one in particular, I would like to teach you, for example, how to unitize a vector, how to calculate the length of a vector, how to set the length of that vector, how to add two vectors together, how to create the cross product between them, and how to tween two vectors and create an interpolation between them. Okay. My purpose in this video is to not get too deep into the underlying geometrical concepts behind these operations, but mostly teaching you how to use Rhino Common to perform these operations and how to learn from the documentation how to do them. Okay? So it's going to be hands-on. We're going to do it together, and it's going to help reinforce everything that we have seen before in the previous videos. So let's talking and more coding. Let's crank some vector algebra components. Beautiful. Let's get started. So as you already know, over this series, what I intend to do is to slowly, incrementally build up a Grasshopper plugin that I think we're calling it Parametric Camp Toolbox or something like that. It's not going to be very useful because it's mostly going to be components that replicate vanilla functionality, but at least it's going to be a way of teaching us how to build a Grasshopper plugin. And if you remember, I was saying that the first large step we're going to do is that we're going to prototype all of our components in C#. And then at some point, as soon as we learn how to transition to native plugin development, we will just take the code and we will port it, all right? So in the previous exercise, we created a bunch of utility components that just did arithmetic operations, string operations, and numerical sequences. And in this exercise, we're going to create a new category in this future plugin, which is going to be for vector algebra and vector components. And what I have done offline, you haven't seen me do this, is I have taken all the components that we have developed in the videos, in the previous videos, so constructing a point, deconstructing point, constructing vector, constructing vector with 2 points, planes, etc. And I have brought them into this file. I'm going to be building this example incrementally. And what I would like to do in this exercise, as I just explained, is I'm going to add more vector functionality to my plugin, aka I'm going to add more components that do vector algebra. The ones that we have seen in the previous videos are pretty straightforward, creating points, creating vectors, and what they mostly use is basically forms of accessing some kind of constructor that instances new objects of type vector 3D, point 3D, plane, whatever. Okay. In this exercise, I'm going to focus perhaps a little more on things that we can do with those objects once we have created them. Okay. And because you know me already and you know me like the things that I like, maybe I'm going to focus particularly on vectors because I think that vectors and vector algebra is extremely important for computational design. That's probably one of the reasons why they call me Dr. Vector in the first place. And the first thing that I would like to do is, given a vector, any vector, I would like to compute some calculations to find its length. So I'm going to create a component that is going to compute the length of a vector. How are we going to do that? Well, very similar to what we have done before. So I'm going to create a component here. I'm going to do this a little faster because we're a little bit more familiar. The input is going to be called L, the output is going to be called, the input is going to be called V, the output is going to be called L, and I'm going to type the input to be of the type vector 3D. And when I double click here, you can see that I have a very simple component that I'm going to actually copy this because I'm going to be using it a lot, all right? And okay, and then here we go, all right? So as I also said in this series, I'm not going to focus too much on geometry or explaining geometrical processes. I have other series and other videos for this. So I'm going to go a little bit faster on the geometrical aspect of things. I'm not going to stop too much to explain this. But sufficient to say that there's two ways I could calculate the length of a vector. I could do the square root of all its components squared. So for example, I could say double length is going to be equal to math the square root of bx times, where is, sorry, vx times vx, okay, plus vy times vy plus vz times vz. So that would be the way to do it manually, okay? And then I could just output here length, so the value of that variable. Let's see if that works. So I'm going to create a vector, for example. It's going to be this one here. I'm going to take it inside a parameter, and then I'm going to internalize so that I can just move it around, or maybe I don't even need to internalize it. I just do it like this, and maybe I dim the cable so that it's a little fainter and it's not so obtrusive. And then I'm going to plug it in here. And then I'm going to plug a panel, and it's going to give me the vector length. And just to make sure that things are working, I'm going to calculate for, where is this? The vector length. So I'm just going to use the same vanilla component to see if the calculation is correct. And you can see that, good thing, Dr. Vector knows how to calculate the length of a vector, right? Good thing. All right, I'm just going to rename this vector length, and I'm going to drop the paint bucket so that we have that. Okay, now that would be the way to do the manual calculation. But I'm actually quite interested in teaching you how to do things in the Rhino Common way. So for this series, for example, what I will do is this, I'm going to cancel this. This is going to be the algorithm manual. All right. And then this would be the algorithm Rhino Common. Okay. So here, what I would do is I would say, well, instead of calculating the length of a vector by doing it manually, turns out that vectors have a property called length that I can just read. So for example, if I do v dot, at that point, and you can see that IntelliSense is already pointing at what it thinks I'm going to be looking at, because this thing uses a little bit of AI and Markov chains. So it's already suggesting that there's a property called length that internally computes, makes this calculation, and returns that value to me. So by using this, I can already save myself a little bit of typing and already access the value of that, of the value of the length of that vector. What's interesting is that this is very good for us to know as computational designers, but if we are already working in an environment that has a geometry kernel that gives us this kind of utilities, like Rhino Common inside of Grasshopper, or like the Unity engine if we were in Unity, for example, then we can also use that. You know, why not? Okay, so that is how we can calculate the length of a vector. Now, there's a couple other things that we can do, which is we can also say whatever we can also set the length of a vector. What that means is that if a vector has a direction and a particular length, what we can do is we can take a vector and we can change the length of that vector to keep pointing in the same direction, but with a new length. So I'm going to create a component for that. And that is going to be, again, I'm going to create an input. That's going to be V, and that's going to be of the type vector 3D. And the other input is going to be called, for example, L. And that is going to be of the type double. And then the output, I'm going to call it V out. So, because remember, we cannot have V and V as inputs and outputs. We cannot have the same name. Vector length set. I believe, or I'm going to rename this, for example, set vector length. And I believe this is the same functionality that the amplitude component in vanilla does. So I'm going to copy this thing, this vector here, I'm going to plug it in there. I'm going to drop here a slider. I'm going to plug it in here. And we can see that we don't get anything right now. But I'm going to try to see if we keep using the other component, what do we get? And this would be the vector that we get using the vanilla component. Let's see if we can replicate that. So I'm going to copy this panel here and I'm going to paste it in here. So what am I going to do? I'm going to do the following. I'm going to go here, double click, and then you can see that my inputs are correct. I have the vector, I have a number, and I have the output, which is V out. And you can see that I'm going to do it also again in two ways. I'm going to do the manual way, and I'm going to do it the Rhino Common way. What would be the manual way? The manual way, it is to actually calculate the length of to actually calculate the length of the vector. And then what we do is we calculate how that length relates to the new length that we want to compute. So for example, what I can say is I can calculate a number called factor, which is a factor is going to be how much bigger or how much smaller we want the original vector to be based on the length that we have right now and based on the length that we want it to be. If you think about this, this is just a proportion. So if it turns out that the L turns out to be twice as big as the length, what we want to do is to multiply the vector by 2. So that's why factor is the length that we want divided by the length that we have. And then the only thing that we need to do is we need to create a new vector, vector 3D new v is going to be a new vector 3D, which is going to have components which are going to be factor times v dot x. So the coordinates of x multiplied by the factor. Factor times v dot y. And then factor times v dot c. Okay? And if that is correct, let's see how we're doing here. Let's see my algebra. And it turns out that, yoo-hoo! Turns out that that approach is the same one. Okay? Now, how would we do this instead of the manual way? How would we do this the Rhino Common way? Well, first of all, because length, the length of a vector, is a property, so we might be inclined to say, well, maybe what I want to do is I want to say the vector that I have, can I choose length? And then can I just say that length should be equal to the value of L, whatever they're giving me from the outside? So let me also please turn this off. So let's see if that is work. If I hit play, you can probably see that the component goes red right away. And why is it that it goes red? Well, this is one reason, but let's see. It says here that the property length cannot be assigned to. It's just read only. What does that mean? Maybe I'm new to Rhino Common, or maybe I'm still figuring out my C# programming. So let's take a look at what that means. What that means is that if I go to the vector 3D structure in the documentation and I start looking for the length property, I can click on the length property, all right? And if I look at this description here, this description is very interesting because what it tells me is length is a property, is of the type double. So whenever I call it, it's going to give me back a double number. But also what I can see here in between the curly brackets is that it's only a get property. What that means is that I can only read from that property, but I cannot write to that property. I cannot just say set, or I cannot assign a value like I have done here, because this is only for reading. It's not for writing. So that's why this line of code is not working. Okay? The option to do here would be something different. What we could do here would be would be the following. What we could do is we can think about what is the process, what does the process of what is the process of setting a, a, let me say this again. What does the process of setting the length of a vector means? What it means is that whatever the length it was before, we just want to amplify it to a particular value. So what that means is that one way to do it is typically very easily to just say, whatever the vector is, whatever the length, I don't care anymore. I'm going to reduce it to a length of 1 unit. And then once the vector is reduced to the length of 1 unit, I'm going to scale it up to the length that I'm looking for. So I'm going to multiply it by that length. So how can I do that? So let's see. The first thing that I can do is I can say, I'm going to unitize this vector. And what I'm going to do is I'm going to say, is there any way to unitize vectors? If I do v dot, what you can see is that, first of all, there's a property that tells me whether if this vector is unit or not. That could be interesting, but not for us right now. There's another one here that says unitize. Okay? And for this one, I would like to read the description very carefully. It says that it unitizes a vector in place. What it means is that it doesn't return a new vector of length 1. It unitizes the vector that we call this method on. Okay? And one thing that we could notice here is that, in fact, the return type of this method is not going to be a vector. It's also not going to be void. It's not going to be null. It's going to be a Boolean. Why is that the case? It is the case because it turns out that this method returns Boolean, returns true or false, whether if the operation succeeded. Because it turns out that this operation may not succeed. There are cases where a vector cannot be unitized. And one such case, for example, is if the vector has components 0, 0, 0. If the vector is a 0, 0, 0 component, there is no way it can be unitized because we cannot divide by 0 length. Does that make sense? So this is a way to have a method that works and returns two different results. The operation that it does, the unitization, but also a flag indicating whether if it works or not. And this is very useful because sometimes you want to know if the vector unitized or not and be able to respond to those kind of errors. So what I'm going to do is I'm going to unitize the vector. I don't need any information. The vector unitizing is just an operation. It doesn't need any additional information. And then after that, what I can do is I can scale the vector by the factor. So let's do this. The next thing I'm going to do is I'm going to scale the vector. So I'm going to say, I'm going to create a new vector, which is I'm going to call new v. And I'm going to say this vector is going to be equal to a vector that is the unitized vector v, the one that has already the direction that I care, multiplied by a number. So if I multiply L times V, which is also a Rhino Common operation, multiplying a vector by a number is something that we can't do out of the box. But because of the reasons I explained before, operator overloading, we can do this. And the result of this operation will be a new vector that will be returned, and that will be the original vector scaled by a factor of L. Okay? And then if I now output this new V, let's see if that works. I'm going to hit play, and you can see that it executes and the result is the same. So yoo-hoo! So we were able to unitize this vector and then to scale it up to that particular length. The next thing we're going to do is another operation that is super, super common and that we have done it. Actually, perhaps we should have done it before, which is unitizing a vector. Okay? So that is also an extremely common operation. So let's see. So what we can do is we can, unitize a vector. So yes, so we're going to take a C# script. We're going to take The input is going to be v, and it's going to be of the type vector 3D, and the output is going to be v out. All right, and then this is going to be unitize vector, and then there you go. And then we're going to take this vector and we're going to unitize it. And sorry, we're going to take another vector that we're going to move here. We're going to unitize it. And then we're going to compare the result with the unit vector, which also I believe is the component that we kind of want to replicate here. So this vector unitize is going to be this one. Okay, so we have done this before, so I'm just going to copy paste a little bit here. The manual algorithm would be Control U to uncomment. The manual algorithm would be something like this. I can calculate the length of the vector, and what I can do is I can divide each one of the components of the vector by the length. So what I can do here is I can create a new vector. I can create a new vector where each one of the components is going to be the original component divided by the length of the vector. So I'm going to say Vy is going to be Vy divided by length, and then factor is going to be equal to blah, 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 divided by length. Okay? And then I'm going to comment this, Control K, Control C, and then you see that the output. And the output is the same. Okay? But if I were to do it in the Rhino Common way, as we have seen before, this, I don't need this, so Control KC, and then what I need to do is I just need to say, well, I'm going to unitize the vector, and then the result is going to be that I'm going to output that unitized vector. And if I do that, I should also get similar results. So I'm pressing run, and then it's also working great. Okay, beautiful. We have vector. We can unitize vectors, we can calculate the length of a vector, and we can set the length of a vector. What other things can we do? Let's try, for example, adding two vectors together. That one is going to be so simple, I'm just going to basically just do it here. So I'm going to say vector A, type hint, vector 3D, vector 3D for vector B here, and then vector V as an output, and then it's going to be called vector addition. All right, and then what I'm going to do here is that I'm going to take two vectors. So for example, this one and some other vector. I'm just gonna add the two vectors that are the same. It doesn't really matter. So, and then what I'm going to do is I'm going to place here a panel to check the result, and I'm going to compare it to how it would be if I were to do it. It turns out that vectors can be added with the addition component as well, so in vanilla Grasshopper. So let me replicate this. And for this, we're not even going to follow the structure. Oh, what have I done? No. So I'm just going to copy this structure, the manual algorithm, and so how would we do it manual? How do we do it Rhino Common? And what are the outputs? Okay. So manual, how would this be? Well, I'm going to create a new vector 3D that is called sum, and that's going to be a new vector 3D, which is the component, the x component of A, so A dot x, plus the x component of B, so B dot x. Then the same for y, the y component of A dot y, plus the y component of B, so B dot y. And then A dot C plus A B dot C. And then the result here is going to be sum. If I now execute this code, something is broken. What just happened here? Name v out does not exist. Yes, I need to, because I was copy pasting, I need to rewrite this, and now I'm going to press run, and you can see that the result is the same. But if I were to do this the Rhino Common way, it would be just as easy as saying vector 3D sum is going to be equal to vector A plus vector B. It's just as simple as that, because Rhino Common gives us this way of adding two vectors together with the plus operation. Okay, I can do that, and then that works. And you can imagine how we can add vectors, subtract vectors, multiply vectors, divide vectors, but I'm not going to do that because, I mean, it's just the same thing, just change the sign. So I'm going to leave that up to you, the viewer, to do it on your own. All right? Something that we can do also quite interestingly is going to be to tween a vector. What does tweening mean? Tweening is typically an alias or a nickname that we use for interpolating between two different states. So if we say, can I tween between two different vectors? What we're kind of saying is, imagine I have one vector like this, and I have a second, which I'm going to assume is the starting state. And I have another vector that looks something like this, which I'm going to assume is the end state. Tweening means creating an interpolation between those two. What that means is typically saying that we have a number that defines how far along that interpolation is. And that number, we typically normalize it. We typically say, well, we assume that if we are at interpolation state 0, then we are at the original vector. So 0 means the original vector. 1 means the end vector. And any value in between means a vector that is slowly interpolating over here. So this could be 0.25, this could be 0.5, and this could be 0.75, for example. So what this means is that we want to create a component that we give it two vectors, and that takes two vectors as inputs and takes another number with decimal part from 0 to 1, and then returns a third vector, which is that interpolation between the two states. Okay, so let's do that. So I'm going to, I can keep this here. Why not? It's not, I mean, it's really bad drawing, but why not? Okay, so I'm going to do that. So I'm going to say component, and this is going to be, this is a new vector component that is not available in Grasshopper. So we are starting to add our own opinions here. So A is going to be, for example, not point 3D, sorry, it's going to be vector 3D. B is going to be the other vector, the second one. And I'm going to add a third parameter that I'm going to call T, which is going to be where I am between those two states. And T is going to be of the type double. And the output here is going to be uppercase V. Now, with this, what I can do is let me figure out some data here. So I'm going to do one vector, and I'm going to say, what is the other vector? The other vector, I'm going to take it from here. So I'm going to take this vector, and I'm going to say that the wire display is faint. Okay, and then this vector is going to be here, and I'm going to just drop here a slider. And just to make sure that this works, well, we're going to do it first, okay? And then we will visualize it to see if it actually works. So I got everything working here. So let me then punch some code inside here. So how are we going to do this? Well, turns out that as per the diagram that I drew before, it's actually quite simple. The only thing that we need to do is we need to figure out for the value from 0 to 1 where we are along this virtual line. So what that means is that we basically have to create a line. One way to do this is to create a line between these 2 points and then find where we are along that line. Or we could do this numerically. So we could just calculate the difference in the coordinates of vector A and vector B, and then multiply those by the factor. So let's just do it the so let's do the manual algorithm, which is going to be double the difference between the two vectors is going to be Vx minus Ax. All right, and I'm going to copy this 3 times. So the difference y, the difference z, this is going to be y, this is going to be y, and this is going to be c, and this is going to be z. Okay, and then what I can do now is I can create another vector that is going to be the coordinates of this vector, this xy, plus this difference multiplied by how far off we are. So that if we are at 0, the new vector will be exactly the same one. But if we are at t1, the vector will be all the way here because we have added the full difference. So vector 3D twin is going to be equal to a new vector 3D, which is going to be the coordinates of a, so a dot x, plus t times dx. So the difference between the two times the interpolation value. Okay? So I'm going to do it a little fancy here. So I'm going to do a dot x, a dot y, a dot c, and this is going to be dy, and this is going to be dc. And I'm going to close the parentheses here. And then the outputs are going to be v equals the twin variable that I just created. Okay? This will be the manual way of doing it. So how can I verify now that this makes any sense? Well, first of all, let's take a look at the first vector and let's take a look at the second vector. If at 0 we are on the first vector, that should be correct. And if at 1 we are the second vector, that should also be correct. So it looks like this is working right now, but just in case, we would like to verify this with visually. So I'm going to say display vector, and I'm going to display this one, I'm going to display the second one, and I'm going to display the output. And I'm going to display all of them from the center of coordinates. So you can see that I have vector A, vector V, and the twin one. And if I switch between 0 and 1, you can see that I twin between the original and the target, the original and the target, the original and the target. And as in the previous examples, we can also go out of bounds of this one. So I can set a value of negative -1 to go beyond, and to go before, and to go beyond. That also works. All right, but that was the manual way of doing it. How could we do this with Rhino Common? Well, similarly, algorithm Rhino Common. There's a bunch of ways that we could do, but I think the easiest one, because we have the two vectors here, is going to be to create a point, to create a line between them two, and to find a point along that line. So I'm going to comment this out, Control K C, and then here I'm going to say, I'm going to create a new line, which is going to be between A and B. But because these are typically points, let me see if this works first. So let me see, this doesn't work, and I cannot convert from vector to point and then twin. Exactly. So these 2 points, these are not points, which is what line needs. These are 2 vectors. So we're going to need to do some translation between these 2. But now that I'm thinking this through, I actually think there's an easier way of doing this with Rhino Common, which is going to be the following, which is going to be, if I have vector A and I have vector V, B, I can find vector C, because C is equal to vector B minus vector A. And then if I multiply vector C times the t value, then if t is 0, then vector is going to be 0, and if t is 1, it's going to be all the way here. So the resulting point can be the addition of A plus vector C multiplied by how far away we are in this line. Okay? So I think I'm going to do that form instead. So let's do that. So what I'm going to do is I'm going to say vector 3D AB is going to be a vector. I'm going to call it C to be consistent with the B is me minus A. And then vector 3D tween is going to be equal to vector A plus vector C times T. And all of this is possible because Rhino Common allows me to add vectors, to subtract vectors, to multiply vectors by scalars so that you amplify or reduce their lengths, to add them together, etc., etc. And I believe this should actually work, correct? I believe so. So if let me check this graphically, if it works. So this vector here, now that we are going to 0, it is right there. Now that we're going to 1, it is all the way at the other one, and then beyond and before. All right, beautiful. So that's how you can twin two vectors together, for example. Beautiful. And last but not least, let me clean this up a little bit. Okay, let me clean this mess here. And last but not least, what I would like to do is I would like to show you how to compute the cross product of two vectors. Okay, if you are not familiar with this, the cross product of two vectors is a third vector that is perpendicular to the first two and whose length is equal to the area of the parallelogram that they both form together. Okay, why is this and where is this coming from? We're not going to get into in this series. If you're actually interested in that, make sure to check my lecture on my Harvard GSD class, Introduction to Computational Design, and the link should be popping somewhere in the car, or it should also be here somewhere in the description. Okay. But what's interesting about the cross product in Grasshopper is how we actually compute that cross product with Rhino Common, or more specifically, the syntax that we use to do that, which is a little bit special. So let me show you that. Vector cross product. All right, and then this is going to be V. All right. So I'm going to plug in, I'm going to copy paste these two. I'm going to plug them here. I'm going to plug the other one there. And I'm going to compare the result with the cross product, which is available out of the box. So cross product, and you can see that this is the result. Okay. And then you can also see that this component, the vanilla component, gives me the length of the vector and gives me the opportunity to unitize that output if I want it or not. And so if I click here, if I put a toggle, you can see that now the output is not going to be unitized, but if I turn it on, the output is unitized. And then the result of this is 1. This may actually be an interesting thing to implement here. So I'm going to start first with the cross product, and then I will be implementing that unitization. Okay, so this one we're going to do it. I'm not going to get into doing the cross product manually. We're only going to do it the Rhino Common way. So if I didn't know how to do that, one way that I can just find how to do things in Rhino Common, in the Rhino Common API, is just going to the search box and typing here, for example, cross product. And then if I do that, you can see that the first thing that comes up is the vector3d.multiply operator. And this multiplies two vectors together, returning the dot product. This differs from the cross product, so warning, this is not what I want to do. So let me go back to the structure, and maybe I can find a method that is the cross product. I just search for cross, and this is what showed up. So maybe in the search, if I had used one word instead of two, you see, I would have gotten vector3d.crossproduct, which is what I was looking for actually. Okay, so we can see that the vector 3D struct has a method called cross product. So let's see how to use that. I'm going to go here and I'm going to say, I'm going to write the algorithm, and then I might be tempted. Oh, I forgot. Can you see how the inputs are object and object? This is because I forgot to type them. Remember, I forget this all the time, and you'll probably forget it as soon as you get, before you get a bit more practice. So A is a vector 3D and B is also a vector 3D. So now I double click again and this is working well. Remember, you have to exit the code editor to change the types and then come back in. So, okay, so we might be tempted to say vector 3D that I'm going to call cross is going to be equal to A dot and cross product. Wait, there's no cross product method, but hold on. I thought that in the methods, there was something called the cross product. And let me go back to the structure. If I scroll here, if I go to methods, you can see that the cross product is here, just like get type or is parallel. So if I have dot is parallel, why do I not have a dot cross product? Why is this happening? Well, this is one of the funky things or the special ways Rhino Common is designed. It turns out that the cross product method has this tiny icon here that means that it is static. And the fact that it is static means that instead of being called on instances of objects, so a particular vector A or a particular vector B is called from the global class itself. All right. I'm going to explain that in detail on the next video, what that means, but sufficient to say that the way we do this is that instead of calling it from vector A, what I say is I type the class name, vector3d, sorry, the struct name, and here you can see that I have another set of methods, multiply, blah, 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 whatever, and one of them being the cross product. So the cross product is, now I can make the cross product of A and B. Okay, and the result is going to be, from this operation, is going to be another method, another vector with that cross product. And then here, the output is going to be V equal cross. Is that true? Am I getting the same result here? It is true. I am getting the same result as in the previous one. Okay? Don't worry about that. I'm going to explain on the next video what static methods and what that thing you just saw, which is called the factory constructor pattern, what that means in detail. Okay? And then just to replicate this, I'm going to add another input that's going to be called uppercase U, and it's going to be of the type Boolean, so that it can be only true or false. And I'm going to plug this thing in here. And I'm going to add another output, which is going to be called L. Okay? And that L is going to be the length of the vector. So what I want is to do something where whenever this is true, the vector gets unitized. So that is going to be extremely simple, because now I have U as an input. The only thing that I need to do is I need to say if U equals true, or we know that we can shorthand this. So if we want to, if unitize is true, then what we can do is we can take the vector, which is cross, and we can unitize it. And we call the method. And that's it, because we know that unitize is going to unitize that vector in place. It's not going to return a new vector. It's just going to affect the vector that it is called upon. And now for L, we can say, let's just output here the value of the length of this vector. Okay? I can do that, and then you can see that now the vector has been unitized, same value, and the length is 1. And if I turn this off, then the vector is normal, and the length is also whatever that is. All right. Okay, so I think that was it for me for vector algebra. Let me just move this over here and make things a little cleaner and tidier. And I'm going to make this another group, and probably as soon as I make this, I turn this into a plugin, I will have a separator here. Like, you know, you have these separators here. I will probably do that for these components here. And I will teach you how to do that. Okay. And I think that's it. That covered some of the most basic vector manipulation and vector algebra that I'm going to cover in this example. In the next video, what I'm going to do is I'm going to cover how to create and manipulate more complex data types like curves and B-reps, for example. And we'll do another exercise with a bit more complex generation of those geometries like lofting, like sweeping, or like interpolating a curve through a sequence of points. Okay, beautiful. Thank you very much for watching this video. If you liked what you saw, maybe click the like button, subscribe to the channel, keep watching the videos in this series, or however your form of showing some gratitude or spreading the word about the work that we do here, however you want to do that yourself. Okay, thank you very much. See you on the next video.